In this second question, we have cobalt chemistry. So complete the electronic structure for a cobalt atom. So we know that there's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. So it's the seventh element in the D block. And when you have +3 oxidation number, you lose from the 4s first. So you lose the first 2 electrons from the 4s, and the next one, because you have to lose 3 electrons, so the next one is removed from there. You just get 4s0 and 3d6. So it's still 3s2, 3p6, but now you will get 3d6. Remove the first, remove the second, remove the third. In an aqueous solution of cobalt 2 sulfate, the cobalt forms complex ions. So what you get is cobalt 2 plus aqueous. This complex ions is cobalt 2 plus, surrounded by 6 water molecule. This is a pink solution. As part of the case study, you must know all the color changes. The definition of a complex ion. So you define a complex ions as a molecule or ions. In this case, obviously it's an ion, but there sometimes you get a complex which is a molecule. So it is an ion in this case that have ligands, and ligands have their own definitions, obviously. So what does the ligand do in this case? Like this water here, these are ligands, water molecules ligands. They will form, they have lone pairs that will form lone pair of electrons that form, actually I have too many that in my answer. They have lone pair, they have ligands with lone pairs. I guess that is probably better, and avoid the overuse of that word that, with lone pairs of electrons forming dative covalent bond. If you don't like the word dative covalent bond, you can use the word coordinate bonds, and this is to the metal center, which could be atom or ions, obviously. State 2 chemical properties of cobalt other than, so you cannot say they form complexes that are not shown by a typical S block element. They want chemical, so we cannot talk about physical. Be very careful. Chemical properties. If they ask for physical properties, then we can talk about some other stuff, but chemical properties, so 2 chemical properties. Transition metals complexes can be good catalysts. Transition metal complexes make good catalysts. Well, they want cobalt actually, so cobalt forms cobalt and its complexes, cobalt and its compounds have catalytic properties. In fact, you can see the bottom bit of this question. They say blah blah blah, and then they say, well, actually this is not about catalytic property. I thought I was correct, but anyway, never mind. They do have catalytic properties as transition elements. The second one, chemical properties, is to do with oxidation number. So cobalt can have more than 1 oxidation number. That's what they say, variable oxidation states or oxidation number. Whereas the S block metal, if you are group 1 metal, your oxidation number is kind of limited to +1. If you are group 2 element, then your oxidation number in your compound is limited to +2. So in this next part of the questions, we have cobalt 2 ions. Some of its chemical properties is similar. Only the chemical properties are similar, not the color. So they have their own individual color that you need to know. But here the question is asking you for the formula as well as the type of reactions. They are not asking for the color of the complex. So think about it, yeah? This is cobalt 2 plus aqueous. So that means it is cobalt with 6 water surrounding the cobalt 2 plus center. With an excess of NH3, we know that unlike the copper 2, which have only incomplete substitution with the ammonia, where you only get 4 ammonia jumping onto the complex and you still have 2 more water. So incomplete substitution with ammonia as a ligand, such that you get copper with 2 more water and you have 4 ammonia. That is your dark blue solution. Hopefully you know this case study. That is your dark blue solution with the 4 ammonia and 2 water. But with cobalt 2 plus, you're going to get complete substitution. So when you have complete substitution, This means all the water get replaced by ammonia. So you still have the 6 ligands around you, and ammonia, just like water, does not have any charge, so you still retain the 2 plus charge for the overall complex. This is a ligand exchange, or you can call it ligand substitution. They both mean the same thing. So ligand exchange or ligand substitution, that should work. On to the next part of the question. When you react with hydroxide, just like copper 2 plus, you will precipitate out the metal hydroxide. So here you get cobalt OH twice. So they haven't talked about color, obviously, but this thing here is actually bronze color. When I said this thing here, I meant the NH3 complex here is brown in color. And then this thing here, you started with a pink solution, which is the aqua complex, and then you get a blue precipitate. Okay, and with the Cl minus, it's gonna give you Cl minus aqueous. Okay, actually you use concentrated HCl. That's the best way to do it. Plus the cobalt 2 plus aqueous with the water as a ligand. Chloride is much bigger, so what you get is COCl4 2 minus, just like copper 2 plus, but this one is pink solution, whereas the one on the right hand side is a blue solution. And of course you will kick out the water as well. My equation is not balanced here, so I better take note of it. And when you want to write the actual equation, you have to balance the actual equation. Okay, so don't leave it not balanced there. Anyway, this is a blue precipitate. You can write it as such, or you can write it as cobalt with 2 OH minus, and then you can have 4 more water, just like the copper 2 hydroxide complex, or you can leave it like this. Cobalt 2 hydroxide is perfectly okay. The formation of most metal hydroxide, including transition metal hydroxide, they are going to precipitate out as a solid. Here you're going to get a blue precipitate. This next bit of the question, this is to do with S2O2 minus. If you look under rate of reaction, rate or kinetics topic in A2 syllabus, you will know that iron 2 plus is used as a catalyst to react with this S2O2 minus and I minus. But here, you don't even have the I minus, it's just the CO2 plus reacting with that. And for that 5 mark, the most difficult thing is not the earlier bit of the question, but it's actually this last bit of the question. So the new syllabus will no longer give you a full data booklet with all the E0 values. I suppose for this particular question, you'll be expected to have access to some electrochemistry data. There's the reduction potential. If we look at this thing here, so if I look at S2O2 minus, this is with SO4 minus, and I'll have to gain 2 electron. This is reduction. If I look in the data booklet, which was available at the time that this paper was offered, the data booklet lists all the E0, which is the electrochemical data, in alphabetical order. This is plus 2.01 volt. Since this is my reactant, my reactant is going to be on the left, so this is going to get reduced to this. So this is the reducing agent. The CO2 plus must be the reducing agent. If it is the reducing agent, itself will get oxidized. So we are not looking for CO2 plus on the left hand side in the data booklet. We're looking for CO2 plus on the right hand side, because that is your reducing agent. So what happened with the CO2 plus is that it will go to CO3 plus, going to a higher oxidation number, and that is your E-ox, because loss of electrons is oxidation, and they don't obviously label it E-ox, they show it as CO3 plus electrons, going to cobalt 2 plus in the data booklet, and that is actually plus 1.82 volt. When we show the oxidation, we just label this as E-ox. We never ever change the sign, because later on we're going to be thinking about something called E-red minus E-ox. So your E cell is E-red minus E-ox. When you combine these two equations together, you will see that the 2 electrons and the 2 electrons do not cancel each other out. So technically speaking, you need 2, 2, and 2. And then when you add the 2 equations together, this and this can react to give you CO3 plus and 2 of that. But even though we multiply this by 2, we do not ever multiply this by 2. We do not change the sign there because the erad minus eox already take into account you identifying which one is erad and which one is eox. So looking at that equation, my erad is plus 2.01 minus bracket plus 1.82. Without even doing it, you can see that this is going to be positive. And there is something in the new syllabus, so your calculator will not show you the plus, but as with anything physical chemistry, sign, value, and unit, we know that this is greater than 0. So the E cell is greater than 0. Delta G is also related to E cell now in the new syllabus. So your E cell is greater than 0. Your delta G is equal to, better use a different color to distinguish this thing here. Delta G equal to minus NFE cell. So N is the number of electron transfer, which is 2. F is Faraday constant. Your E cell is greater than 0. So your delta G is going to be lesser than 0. And when delta G is less than 0, as stated in the A2 energetics, advanced energetics, this is also going to indicate the reaction is feasible and spontaneous. So this reaction is feasible, which means what is the formula of the cobalt species that we will get? We will get cobalt 3+. As stated in the data booklet, that is actually cobalt H2O6, but no longer 2+, is 3+. If you don't wish to write that down, I'm pretty sure you will get away with this if you write down CO3+, but you have to include the term aqueous. Why? Because if you read the question, this was CO2 plus aqueous, you have to write CO3 plus aqueous. CO3 plus on its own will not be accepted. This is okay because CO3 plus aqueous basically means it's this complex with the 3 plus charge there. And that's the 5-mark question. So this next bit, we have some transition elements present as superconductors. I don't think we need to know anything about superconductors. We are asked to find empirical formula, the simplest whole number ratio of atoms. So it looks like very, very complicated, but these are scary elements which we don't normally use. But it's okay, it's empirical formula. It's only 1 mark, so let's just get on with it. 13.4 divided by yttrium. Yttrium is just below scandium in group 3. So not group 13, but group 3. So make sure you know your new periodic table. So just below scandium then. Barium is group 2, so 41.2 divided by 137.3. Copper there is 28.6 divided by 63.5. And last but not least, we have 16.8 divided by 16.0. So press your calculator, 13.4 divided by 88.9. I get 0.151 to 3 significant figure. So of course these are 1 mark questions, so I should really speed up and try to get it done and over with. But of course, no matter how much we speed up, we have to try to maintain a certain standard of our handwriting as well as our clarity of our work. So that was just mole concept, and then we have to divide by the simplest ratio. So that was mole. So now it's the simplest ratio. So the smallest number is 0.151 divided by 0.151, which is 1. 0.300 divided by 0.151 roughly give you 2. 0.450 divided by 0.151 roughly give you 3. 1.05 divided by 0.151, that roughly give me 6.95, which is 7. Show that. So again, Y, BA2, CU3 or 7 shown. Shouldn't put a tick on it. It's probably the examiner job to put a tick on the answer. Now we have to calculate an average oxidation number of this copper in Q. So what do we have? We have Y, BA2, CU3 or 7. So looking at that, the yttrium is plus 3 and you have 1 of it. You have 2 of the barium, barium being a group 2, exclusively plus 2 in compound. You have 3 copper, so you know there are 3 copper, and our job is to find the oxidation number of the copper, and there are 7 oxygen, and we have 0 because the overall compound has no charge, no overall charge. Okay, so 3 copper equal to, what do we have here? Actually, what do we have here? plus 3 plus 4. 2 times plus 2 is plus 4, so plus 7. Plus 7 minus 14 is minus 7, so that's going to be plus 7. Copper equal to plus 7 over 3. So they want the average, and they don't want really fractions. They want to calculate. Calculate means not really fractions unless they want it. So I'm just going to express this as a decimal place. So this is plus 2.33. I don't know if that will be right, but it's 1 mark, so I probably get away with it, or I might not. But I have my exact fraction here, just in case the examiner don't really accept this answer. They can have a look at that. But what is required, however, is this signed, because oxidation number must have sign, as you could see, plus and minus, because these are not 0. What do they want? I don't know what do they want actually. Oh, I think I get the idea now. I think they want this one to be here, because they say the average oxidation number of copper. So what they want is really this one here. So the average oxidation number of copper there. So that is just your average oxidation number of copper. Average oxidation number of copper, and then you have 3 times copper. So each one, you see, now each of the 3 is when we divide that by 3. So I'm going to get that final answer here. So realistically speaking, this is not bad for a 2-mark question. And that is the end of that 13 marks rather unusual transition metal question, I guess.